Okay, so today we're going to talk about buffer overflow. Mhm. Uh, well, if you ask me what is buffer overflow, I would say it's classical security problems that has been around for more than 30 years. The point is we still have buffer overflow today. So that's why I think we should learn about the fundamentals of buffer overflow. Mhm. For that, we understand the concept behind the problems, and maybe we can help prevent buffer overflow from happening to our software or our system in the futures. Mhm. This slide actually taken from partly from my thesis, and I rewrite it a little bit for the class. Uh-huh. And it's one slide that I once shared with my professor in the past. I mean, since my PhD is about buffer overflow, so sometimes I got invited to speak about this. And my professor also got invited, so we share the same slide. We just change name when we have to use it, just like that. All right. So first thing I would like to briefly talk about history of buffer overflow. Mhm. So we have buffer overflow, and to be honest with you, all kinds of deadly worms, or sometimes we call it one-day worms, or zero-day worms. They are buffer overflow. Okay, a little bit about the one-day worm and zero-day worm first. You happen to know what is one-day worm? When we call a one-day worm, what does it mean? One-day worm. What is it? And we have also have a zero-day worm. What is it? Well, when we use the word one-day worm, just one day, in a sense, it means that this worm take less than a day to spread all around the world. That's the word one-day worm. But what about zero-day worm? Morning. Ever heard of it? Okay, you got it anyway. Okay, let me explain about the zero-day worm a little bit for those of you who may not familiar with the term. It's like this. Let's say I found a bug in Microsoft Windows, for example. I found a security hole in Microsoft Windows. A proper way to do it is that I would call Microsoft and say, hey, Microsoft, I found a way to hack into your operating system. This is how I get in, for example. What Microsoft will do is that Microsoft will say, hey, professor, please keep it to yourself, maybe for about 3 months. Please wait until Microsoft have a patch for it. Microsoft will fix it. By the time Microsoft is able to, let's say, have a window up there to fix that vulnerabilities, then Microsoft would let me know, and I would say, hey, I found a security hole in Microsoft Windows. This is how to do it. And that's the patch from Microsoft. That's the proper way to do it. If I found something from an issue in a piece of software. But zero-day worm means, okay, I found a security hole. I told Microsoft, but while Microsoft is still working on the patch, on the update, somebody used this knowledge to create viruses or worm. That means these worms got no fix. We call it zero-day worm. It starts at day zero. By the time that the worms spread out, we got no patch like that. The patch would be in the future. That's the term zero-day worm, mean a worm with no patch, something like that. That's another way to explain that. Anyway, you got it anyway. So in the past, we got viruses and worms. And if you ask me, I would say most of the time, if that worms say something like limo execution, it's buffer overflow. So when you see limo code execution, likely it's buffer overflow. So we learn about buffer overflow. We first learned about buffer overflow in 1988. This year is what? 2000? 30 years, about 35 years, like that. And we still have it. That means it is something fundamentally wrong that we still have buffer overflow today. Anyway, the first computer worms is Molly's worm. If you don't know, if you like history, Google for it. Molly's worm. Look for it. Well, actually, Molly's worm is created by a person named Robert Mollis. His name is Robert Mollis. And when he created that worm, he actually was a student like you, college student. And he learned about buffer overflow, but he used a vulnerability in a piece of software called Fingerd. If you are a unique user, you would know that the finger tools allow you to see who is online on another machine like that. So he sent a finger command to see who is online. And I want to talk to that person like that. But rather than see who is online, his code allow him to run whatever command he wants on another machine. So he infect his code to another machine and use it to infect another machine and so on. So back then he was able to infect about 10% of computers on the internet. But we talk about 1988. Back in 1988, if you want to use the internet, you may have to go to public library and use the Unix machine. If my memory serves for our university, I wasn't a student here yet in 1988, but back then, like for our university, we have only one Unix machine that's shared with all people on the campus located at the main library, like that. And he was able to infect 10%, and 10%, that means he conquered 10% of Unix machine in the world. That pretty much main university. Well, a little bit about Molly's worm anyway. By the way, Mr. Robert Mollis is still alive. Okay, he's still alive. And in case I want to guess, where is he right now, Robert Mollis? Anybody want to guess? Where is Mr. Robert Morris, the person that created Morris worm? Uh-huh. Well, my professor used to say this is $1 billion questions, but I didn't agree in any way. But Mr. Robert Morris, nowadays he's a professor at MIT in computer science. Mhm. And a little bit of a history when he created this firm, it was like his personal project. He do it for fun. Uh-huh. Just experiment with his code, and he was able to infect code to another machine. But there's a bug in his code. Mhm. Normally, if he got it right, it would infect his code to the target machine, and then use the target machine to infect another host, and terminate itself. But he did something wrong. So rather than terminate itself, it would fork itself several times. So people wake up and try to log into the computer, and people would see, oh, there are some strange process, thousands of processes running, and the machine was so slow. So they know that something was wrong with the machine. Again, we talk about 1988, not that we have gigabyte of memory. Back then, we got just megabyte of memory. So that's how we will find out that, oh, something bad happened to the computer world. And we call that the first worm. And it was on the news, on the radio, that, oh, something bad happened to several computers in United States. When Mr. Morris learned that, oh, he might did something wrong. That caused several computers around the world to slow down and got an issues. What he did is that he told his father, who happened to be a professor in computer science as well. He told his father, hey, Dad, you see the problem with computer around the world? I think I did it. If you happen to be his father, what will you do? Well, his father called an FBI, and said, FBI, you heard from the news about issue with computer around the world? I think you want to talk to my son. So FBI take Mr. Robert Morris in, and we learned about Overflow from that. Anyway, I didn't follow through the cases, but if my memory serves, Mr. Robert Morris got sentenced like something like he cannot touch keyboard for 6 months, something like that, or have to do public services for his crime on creating the first computer worm. Again, this is 1988. If you do something like this today, you go to jail. And after that, this is the name of, I would call one-day worms or zero-day worms. We still have a lot until today. I got lazy and don't want to put in too many names on the list. But if you look behind those worms, whatever the name is, it's actually buffer overflow. Just like that. And yeah, this is some of them. If you go to search, and you search for buffer overflow, you see long list of that. And this is one of the worm that took down the nuclear power plant in the United States several years ago. That's also buffer overflow. This is the slammer worm. Well, a little story about this worm. This happened in 2003 anyway. We got nuclear power plant in Ohio State. in the state of Ohio in United States. Well, Ohio is kind of Middle East, Middle West. Well, the United States, they call it Middle West, but it's not that West anyway. Kind of in the middle of the country. And if you draw the map of United States a little bit, you would see that United States got several time zones, about 5 time zones. Ohio is here. This is Ohio, around that. So since United States got several time zones, so it's like, oh, this is afternoon, this is still morning. Oh, this is night, this is still evening. So it's night in New York, it's evening in California, like that. This nuclear power plant in Ohio, they somehow managed to run on Windows 2000. They use Windows 2000. The whole system runs Windows, but they have this isolated network, isolated system. You cannot use USB drive, you cannot use CD-ROM, you cannot, no network connection at all. So there is no way that this network would be infected with any worms or virus. But what happened is that they allow contractor to make a modem dial-up call and switch the power. So the nuclear power plant kind of run 24 hours, right? But during different times of the day, they spread power around the country. So in the evening, they may spread power here, but later they would switch it back here. So they allow contractor that make a modem, a 56K modem call to switch the power. And that's how the worm got in from the modem line slow network. So when the worm got in, it spawned process and it shut down the database server. And the safety protocol of the nuclear power plant, should something bad happen, it would shut down the system. So they simply just shut down this system. And when it shut down, they got widespread power out throughout the east side of United States. So we got back out for about 10 hours like that. And I was there. I was a student there. And during that day, I know that I have nothing to eat because I went to grocery store and they cannot sell anything. They say the registration, the cash machine isn't working. I want to buy something and they say, no, it's not working. And my apartment back then, the heater, everything, it's electricity. We don't have electricity. So I stay cold in my apartment that day for several hours. You learn later that, oh, it's this one that caused the issues. Like that. It caused outage to several things. Shut down the internet, shut down the banking machine, several things. That's also buffer overflow. Several cases about buffer overflow. Anyway. Okay. So we learned how bad buffer overflow can cause us. We learned that several worms and viruses, they use buffer overflow to get in. So what is buffer overflow then, and how does it work? Okay, let's start with this simple example. Okay, I give you few minutes to make sense of this code. Okay, pretty simple, right? So it would print this, and you type in your age, convert to integers. It would print this, you type in your name, and it will print you are that years old. So okay, let's try run this. I run this. Where is the problem? Yes. Uh-huh. Yes, you got it. Okay, for those of you who may not see that there is a problem here, I first type I am 15. Somehow it changed to 49. And as suggested by our colleague, this is 8 characters, but if you count this, 9. So it's like this. When you type the name, it would go here. But when you type long name here, it overflow. So it overflows on top of another variable. In this case, the variable age. Yeah. Yes.
So, since the program why the program had the ASCII values of the characters of
Right. And since this is Intel, and Intel use little endian, so number one, the ASCII value is what? Sorry, the ASCII value is 49. So that's how you get 49. Or in hex, that would be 31 in base 16. 49 anyway. So that means if I change this to number 2, this would be what? 50. It is straightforward. Right? Or if I change this to letter A, this would be, I cannot remember, 64 or something, 61. Anyway, I cannot remember the ASCII value of A. This is buffer overflow, basically. So from the name, you can guess, I allocate 8 characters. I write longer. It goes somewhere. Where? Here. To the adjacent variable, in this case, age. So I can change age without directly access the age variable. Yes. What? Name.
after point you want to
1, 2, 3, 4, 5, 6, 7, 8, 9. Name what? In the final sentence, yes. The whole name is bigger than that, yes. Oh, okay. The printf would print until it's find the null terminator. Yeah. Right. So the printf don't know the size of name. It will continue printing until it's find the null terminator. So it continue printing the whole name. But the age variable say we start here, we will read 4 bytes and see it as an integer. And this 4 bytes happen to be the convert of hexadecimal to decimal. The conversion of hexadecimal to decimal. Yes, please.
What you see, but for format, they print the corporate names, but one that it because of the book of so what why is it is not why it is the way you expect it to understand what one is to present, why it's
I cannot hear you clearly, sorry.
So the one in your name is in front outside your from name. So why you put that is in I expected print that to print your name on zero and not on 1.
Oh, why not 0, 1? Is that what you say?
Yeah, there was one extra character in the output like this.
So the person S suggests that this is a string. So we continue reading it until we find the null terminator, which is 0 in this sense.
Okay, even if it's our set.
Right. Right. That's it doesn't care about the size of the buffer. It would continue printing.
Okay, so we have to check on the length of the
Okay. At the machine levels, they didn't have notion of the size. They just keep continue printing until you find the null terminator. Same things. I mean, if you're familiar with C programming, you may start with, pointer S as the character. That's basically string. You seeing okay?
Yes.
Characters star S, that's the pointer. And you can say S equal name. So it has no notion of size. You just keep using this as a string, just like that. Sometimes people say Buffalo is a bug in C programming language, maybe, but no, some say it's a features. Pointer in C, you can treat anything as a string. Just point to that memory and use that chunk of memory as a string, like that. Okay, very good. This is the C programming. Okay. Well, how bad is this buffer overflow? Not so bad. In a sense, it's just, in this case, make me older, right? Change my age from 15 to what, 49. But that means I can now write to other variables without directly access that. So how bad can it be? Okay, let's see a little more advanced version here. Not sure whether you're familiar with the parameter passing or not, but let me try to explain that so you understand how does it work. So it's like this. When you have parameters, or you may call it agreement, to a function, when you pass an agreement to a function, what happened is that they put that agreement on top of stack. So in this case, they would put pointer b and integer I on top of stack like that. And then when you make a call to this function, we would have a return address. Okay, I think I have to explain this. Let me ask this first. What is a return address? You know the return address, right? Do I have to explain that in details? Are we good? Okay. Okay, maybe I do a quick version for those of you who may not familiar with that then. Okay, I got an empty page here that might help. So let's say you write a software. You may say, I don't know, I equal 5, whatever. And then later you have a call. Let's say I call printf, like this. Okay. And then I continue doing something after that. What happened is that if we translate this into maybe assembly language, low-level machine code, it would have a call to some function. And that function is actually located somewhere else. Right. Like that. It's actually, eventually it will translate to address. Like this may be another address, so we replace with another, just number. And as we execute this function, eventually we would end the function with an instruction like return. Where do we have to return to? Well, it's return here. Right? I call you, you do something, you finish, just come back and I continue working. So that means whenever I make a call, I have to remember that I have to come back here. That's the return address. And what is the best place to store that? We got a special kind of memory we call stack. And stack means last in, first out, right? So I keep pushing, let's say our stack grow from top to bottom, these pictures. So whenever I make a call, let's say this is maybe address 44,000, okay? So that means I make a call, I have to come back to 44,000, so I have to put 44,000. And when we have return would look for 44,000 and get back here. Okay, so how about what if in this function, I make another call somewhere else? I also have to remember where to return, like let's say it's 8100. So I have to put down 8100. So this call would return here, and then this return will return back here. Keep stacking down, and when you return, you kind of push it back. But we also use this stack for other things, like if you have local variables here, they would allocate space and use as a local variable as well. So that's how parameter passing or recursive call, function call make use of local variables. They use special kind of memory they call stacks. Going down, make a frame for this call. If you have another call, make another frame for it. And when you return, you clear this frame and you return back. It's like that. Anyway, what we just draw, this is the one frame of a call. So we got pointer P, you push P to stack, you push I to stack. And then when we make a call, we save the return address, but return address, the Intel architectures use the word EIP for return address, which is short for instruction pointer. Okay, for those of you who are not familiar with Intel terms. Well, other processor, usually they call PC, program counter. But Intel got funny name for it, they call it instruction pointer. Yeah, well, it's according to history, Intel used segmentation when they first designed the processor. So they call this code segment and call everything that point into the segment a pointer. So that's why they call it instruction pointer. But other processor that doesn't use segmentation, they call it program counter, just like that. Basically the same things, just different term. And when you have J, foo, FP, whatever, it would go here, right? So we would have J, foo, FP, and we eventually have buff B here. Where it would go backward because the stack go from top to bottom, so it go backward like that. Okay. So how bad can this be? Well, we got what? We got string copies. We got string copies. And we got string P that the bad guy can pass to you. Again, C string means starting from wherever you want and keep going until we see null terminator. So it can be infinity size in a sense. Keep going until we find the null terminator. So we have string copy that would basically copy string from P to B until we find the null terminator from P. So no bound checking in a sense. Keep copying until we find the end of the string. So this is what the bad guy can do. Make very long string, pass to this function, pass it to this function, right? And if you do the calculation right, you would be able to replace the return address. That means at the end of this function, when we have the return, now it would return somewhere else rather than return to the code that call it. You would return somewhere. So if I happen to be a bad guy, I would want it to return to the code that I put in. Right? I want to inject a code and make it return to my code. So where to inject the code? Here. Inside the buffer. So I craft a buffer with the code that I wanted to execute. Then I somehow managed to change the return address to this. Once this function call ends, we see the return instruction. Now it will execute my code. Yes.
Before trying to this attack, you have to put your values inside the victim system before exploiting the script.
Do we have to encrypt it?
You put your program, and before, for example, pointing to your program and you have to put your program inside the victim system.
No.
You can understand how is it possible to access something it isn't present on the victim.
I'm not sure if I answer your question right, but you have to do it in binary. Got my point?
If your input, you put, for example, like pointing to your prediction program, how to it, why it is that
Say that again. I'm not sure I understand the question. I'm sorry.
So you have your malicious program to exploit the victim machine. If it isn't present, just the victim machine. Something prevents your machine to create it, that isn't present in the victim machine. How do you program if it isn't present?
Oh, okay. So you mean how would I know the address of this?
Yeah.
Uh-huh. Okay. That's tricky part, yes, but actually it's not that difficult to find the address of this. Because how to say, we can disassemble the machine and we can measure something. Like the software that installed on your computer, likely it's the same software that installed on my computer, the same binary. So I can disassemble the software and learn about the stack layout. Like you learn Windows, I also learn Windows. You learn this software, I also learn this software, so I can learn about this software on my machine as well.
So it's more like accessing something that is present in all machine than accessing something what's in all machine to put the victim machine. Just to know the information on your victims on the computer, and then with this information, you put your malicious program in the victim computer.
Yes, like that. Okay. Anyway, you got a chance to explore that in the activities. I will let you try to do buffer overflow on a piece of software so you understand how does it work, right? But the concept is like this. Bad guy would put malicious code or the code that he wants the victim machine to run inside the buffer and somehow redirect the address back to this. And how to figure out the address, that's the tricky part, yes. But eventually we can make it happen. Okay. Some guessing, some random things, but yes, but eventually we make it happen. Okay. So we point it back. Once we point it back, we got everything. The return function would run this code. So again, if you happen to be a bad guy, what would what kind of code you want to put in. Likely a shell code that would give you maybe a terminal access to run whatever command you want. You still remember the activity a few weeks ago that we do a reverse tail using the netcat? Yeah, sometimes we put something like that in this. It would send netcat back to me. That's one possibility. Anyway. Okay. I got another example which might make more sense to you. Okay. To understand this, you have to understand another concept. We call it jump slot, or some operating system call it a link table. Link table. Okay, let me try to explain the link table first, so you understand this example. Okay, let's say my code use something that we call share library. Shared library. So what is shared library? Okay, simple one. Let's say I use printf. I use printf, for example. Question is, printf, is it my code? Is printf my code? No. I never write printf. I just know that if I call printf, it would print to the screen. It's like you write either in Python or other programming languages. When you use the command print, the function print, it would print to the screen. But have you ever created a print function by yourself? No. You just use it. So I would say any function that you call that it's part of the system, but you never write that function by yourself, it's a shared library in a sense, function that somebody created for you. You just call it. Okay, so in this example, printf is not my code. When I call printf, what the operating system do is that it would load standard C library, libc. And when it got printf, it would call to that function. This is how the runtime environment works. But when we compile the software, we have no idea where it printf, right? Because I didn't run it at the moment, so I don't know where the operating system will load the printf for me. It can be anywhere in the memory. So what it do is it would make a stub, like if we translate it into assembly, it would make a call to something like this, printf. And it would create a table, say, oh, if you want to call printf, we would jump somewhere and leave this open like this. When you first run the software, when you execute this software, operating system would see, oh, we have to fill this table. Okay, let's say we load printf at address 8,000. So we would put 8,000 here. So what happened in action is like this. When you run the software, it would call this function, and this function would jump to the real printf. And when you have return, it would then return here. So that means this part is dynamically bind. because it depends on when you run it. Oh, operating system load standard C library over there. So the address would keep changing. The next time you run, it may load somewhere else. So it keeps changing. But in reality, the operating system just load one copy of this share library and share with every software on your machine. Okay, we call this table sum table, or some system call it link table. Windows also have it, but Windows sometimes use different name for it, like you may heard of the word DLL, dynamic link library, that basically share library for Windows. For Linux or Mac, they use the share object, SO, share object. Anyway, it's link table or sum table, however you want to call it. Okay, so we have link table and sum table. So let's take a look at this. Where is that? Okay, this one. Okay, let's take a look at this example. This is how it works. Again, I kind of reverse this example from one worm that I found myself several years ago. This is how it works. Again, we have a function where a user can pass string basically to this function. We got local variables and we got string copies. So in this kind of attacks, the first string copy allow you to create a pointer to any address. So it would create a pointer to this jump slot. And the second overflow would allow you to change this. So if this is a jump slot for printf, that means any call to printf after this would call malicious code, the code that bad guy want you to call. So you think you call printf, but wait, you call something else. One worm, Apache slappers use this technique. Well, I call it multi-state buffer overflow. I mean, you have to overflow several times until you get to the target address. Eventually, they got it. Anyway, you may find out, what? Why do we have to do that? That's several steps to attack. But again, for the bad guy, they got this sense that they usually say, if there is a way, we will get in. Okay, very good. Again, from the picture, it looks easy. From the side, it looks quite easy, but in reality, it's quite elaborate, quite detailed how to make it really happen. Okay, very good. All right. So far, we have learned about how buffer overflow attack works. So in a sense, it's just you have a piece of code, piece of software that you didn't properly do bounce checking. Somebody sent bad input to you. It eventually changed your program flow to execute the malicious code. Okay, that's what we call remote execution or buffer overflow attack. So whatever you want to call it. But again, the underlying issues is just buffer overflow. Okay, and we have buffer overflow for years, more than 30 years. So let's look at it in another way. How about you want to stop this kind of attack? How to stop it? So there are a few things about it. If you take a look at how it happens, there are actually two conditions. First, bad guy sends something to you. Then that's something the bad guy is able to change the program flow to call that something, to execute that something. So in a sense, it's like, I want to infect you with something. So I send something to you. And somehow I have to be able to fool you to take that. Okay. We have other kind of attack we call integer overthrows and printf vulnerabilities, but I will not talk about it today. But the effect is similar to buffer overflow that I just explained to you. Okay. So that means, okay, sorry, too fast. If you want to stop buffer overflow, you have to stop either here or here. Just take down one condition. Right? You just have to take down one condition. Either stop the bad code or malicious code from getting in, or if it get in, don't use it. You just have to take down one condition, just like that. Okay. All right. This is a part of my survey paper. Anyway, how to protect yourself against buffer overflow. Think about it, there are three main ideas if you want to stop buffer overflow. The first idea, I call it static analysis. Well, to make it short, fix the code. Make sure you check the boundary, the size of the buffer before you use it. Just fix the code. Okay, that's static analysis. See the code, find potential issues, fix it first. Second idea, dynamic solutions. You put some kind of runtime environment, some kind of checking in the runtime environment to prevent the problem. And last idea, isolation or sandbox. Basically, let it happen. Should the buffer overflow happen? Let it be. Just make sure that it cannot harm your system. Okay, so let's take a look at it a little bit. So static analysis, how does it work? Well, in a sense, static analysis basically you give it the source code and it would tell you where is the problem. Like, oh, you have string copies. If you pass this through the static analysis, it would say, no, don't use string copy. You get into trouble. Or it sometimes analyze your loop and say, hey, your loop is off by 1. You may have buffer overflow. But the point is, you just give it the code, the tools will give you a report, and you fix the code by yourself. That's basically static analysis. And I got a list of some tools here anyway. You may have heard of some tools like they call it lint. Basically, just try to analyze your source code and make sense from it. But sometimes we also have false alarm. What is a false alarm? No buffer overflow, but the tools say, no, you cannot do this, you cannot do that. And sometimes it doesn't have the runtime environment, so it don't know whether it got buffer overflow or not. So let me focus on this dynamic solution. Okay, let's try to understand how people try to prevent themselves from buffer overflow attack a little bit. All right, I got 4 ideas here that I want to share with you. Let me pull up big pictures of it so we can easily explain that. Okay, here's the idea. Since buffer overflow only happen in one direction, like you write a string in one direction. So when you have buffer overflow, it's like you overflow from here to here. So to protect yourself against buffer overflow, one idea is that we put some known value in between. And before you use the address, you validate this value. We call this kind of protection a canary. Okay, what is a canary? Ever heard of the word canary? What? A bird? Yes. What kind of bird? You know the canary? No. Okay. Yeah, quickly pull up canary. Hmm. Okay, this is the canary bird, yellow bird. But why we call it canary, or why we use the word canary? Okay, maybe you haven't seen it before, but what is his job? What does he do? Yeah. Okay, I stick with this one really quick. What is a canary? Yes. Anyway, a little bit about history here. Canary bird, in Thai, we call it nok kamin, in a sense, yellow bird, basically. So this yellow bird, it's kind of sensitive to the environment. That means it will die easily if it is in bad environment, like gas leak, too hot, too warm, something like that. So back when people still don't have good technology, the coal miner, people that go down underground several meters, look for coal down there, they would have small cage with canary bird. And if the bird died, we know that we should get out. Something bad is about to happen. The environment is too bad for a person. So we have small bird in a cage. If the bird die, we evacuate like that. So in a sense, it's kind of ancient technologies, how to detect bad environment, gas leak, underground, like that. So don't let the bird die. Don't let the person die. Let the bird die for us. Well, it may sound cruel or something, but people use that for years. And in fact, I think they still use it nowadays. So that's the same idea. We put known value in between. When we have buffer overflow attacks, you just read this value. If the value is still good, okay, we're still good. If this value is changed, no, we are not in good. We might be attacked. So let me give you an analogy for that. Let's say I got a loom. I got something valuable here in the loom, and let's say this is the way in. I want to protect this valuable inside the loom. So what should I do? Maybe I can chalk on the floor like this. Can chalk on the floor. That means if the bad guy got in, I will see footsteps on the floor, right? So if I see footsteps on the floor, I say, oh no, somebody got in. Same thing, same concept. Okay. Now the question. If you happen to be a bad guy, you know that we got some kind of shock protection on the floor or some kind of canary protection. But you still want to get in without being caught. What would you do? Got my point? Got my question? Okay, this is the door in. I got something precious in the other corner of the room. I don't want anybody to get in, so I paint chalk on the floor. You say you want to get to that corner without being caught, without I get noticed that you got in? How? So when you got in, you just paint it back, right? You just paint it back. Now I wouldn't know that you got in. Got my point? How to bypass this canary protection? Just make sure that whenever I do buffer overflow, let's say if the canary is number 5, I would overflow and make sure that this would be number 5. Stay the same. Right? Yeah. And like that, when we have this kind of solution come out, few days later, bad guy say, I know how to bypass this. So this one is not working in a sense. But believe it or not, modern compiler do this. I mean, if you compile your software nowadays, they do this. But can you bypass that? Of course. Okay, let's try this one. Well, this is easy, but let me pull big pictures for that. Yes. Okay, so how does it work? It's like this. We have buffer overflow because we use the same stack for everything. We have parameters, we have return address, we have everything on the same stack. So they just propose, what if we split the stack? What if we have special stack like control stack to save the return address and another stack for data only? So that means even though the bad guy can overflow here, the address is still good. That's one example. Or sometimes they propose a hardware enforced split stack, but that means you have to modify the processor. But is it good? I would say it's good for this kind of protection, the return address. But in reality, we also have buffer overflow on something else that is not the return address. So, okay, we can protect the return address, but not the others. But from my point, they cover one kind of attack, which is the return address attack. but not the jump slot, not the others. And I got a list of several proposals that try to do that. Again, this is a list of several proposals that try to do that, but they fail in a sense, or sometimes they use special hardware on certain processors to protect that. Not a universal solution anyway. Another proposal for that is address encode. Let me pull that out. Big pictures, address encode. This one, okay. Okay, it's like this. The idea is simple. Whenever you put the address to the memory, make sure that you encrypt it. That means if the bad guy somehow managed to change the address, overflow it with that address. Whenever you dereference that address and you decrypt it, it would be random. So that makes it difficult for the bad guy to attack you. Because now, oh, I want to overflow that address, but wait, it's encrypted. That means if I overflow it, then decrypt it, it got some random number. But if you ask me whether this is working or not, I would say, no, not a good idea. Why? Because too expensive. Right? Because now whenever you make a call or a return or jump, you have to do some kind of encryption. Encrypt and decrypt, encrypt and decrypt all the time. Too expensive, let's say. Because we always have call and return in our code. So you cannot encrypt it with something difficult, or else it would take several cycles to encrypt and decrypt. Really slow. That means you have to encrypt and decrypt with something very simple. But again, if you use simple encryption like exclusive OR, that means the bad guy can easily crack it. So this is not working in a sense because it's too expensive or it's create compatibility issues. So far we have these solutions that seems to be easy to implement, but not practical. I mean, not a bulletproof protection. And we have some architectures, like the IBM mainframe architectures. They call it cat architectures. The tag architecture is like this. In the memory, they would got a special flag on top of the memory. So when they create a function pointers or a return address, they would mark it. That means buffer overflow would be protected when it want to write over. So they got hardware protection in a sense. But again, all the IBM got this kind of hack architectures. So you may say that if you use the IBM mainframe, the System 38, you would be protected from buffer overflow in a sense, because they got hardware protection for it. But the downside is these architectures, the IBM mainframe, is one architecture that is difficult to program. Because we got a case where we have a C code that would not compile and work on this System 38. You may have to change your software a little bit, modify the source code a little bit to make it work on this system. And it's not that you have IBM System 38 at home anyway, so it's not universal. So let's try this. Let's pull up the slide. Here we go. Okay. Okay. If you ask me, I would say this is the perfect solution for buffer overflow, because it's fit buffer overflow at the source of the problem. So it's like this. In the past, when we create a pointer in C, they would just make a pointer like this and allocate the space, but they didn't check for anything. They just allocate enough space for you. But the solution is, why don't we make this an enhanced pointer where we have a base address and a limit? So that means your pointer can only go within this space. Bar checking, basically. We have both software version of bar checking and hardware version of bar checking. The hardware version is called segmentation. And in case you don't know, Java, Python, or whatever programming language that they claim to be type-safe programming languages, they do this for you. You allocate a variable, it makes bar checking for you. So if you use programming languages that do this, you cannot write beyond the boundary. The system will automatically manage the boundary for you. So it works in a sense. But whether it's fast, no. We learned that in some cases where we have a lot of pointer, the enhanced pointer can be like 30 times slower. So it's like you run one software within 1 second. If you use the enhanced pointer, it can be 30 seconds. Quite expensive anyway. But whether it's a good solution, yes, it is. But the downside is, if you use the software solution, like if you use Java, Python, that technically speaking, there should be no buffer overflow. The reality is no. We still have buffer overflow in Java and in Python. I'll get to that later. Okay, so this is good solution, but not that every people want to use it because it might slow down your software. And let's move on to the next one. Okay. All right. This is one difficult word to pronounce anyway, but if I got it right, the correct pronunciation is obfuscation. Anyway. So what is obfuscation? Obfuscation is like this. Normally, you can count from the source code how many bytes from the buffer to the return address. Now the obfuscation say we would put some random offset in between. So that way, when I have to do buffer overflow, it would be what? How many bytes? No idea at all. But I can, well, if I happen to be an attacker, I can still keep on writing the buffer until I get it. I mean, keep random writing, futzing until I get it. So obfuscation means you put some confused thing in between. So make it difficult for the hacker to understand the code. And Microsoft also do that. Linux also do that, and they may have different name for it, like they call ASLR, address space layout randomization, something like that. You might have heard of it. We still have it today in our computer machine. They would random some address space and make it difficult to guess. Okay. Okay, let me try to explain this one. Input protection. See, I have pictures of it. Okay, let's see. Okay, let's try to understand this picture a little bit. All right, this is how it works. This is actually a part of my thesis anyway. So here's the idea. I modify the memory layout and the processor to include one bit similar to the tag architectures, like that. And whenever we have input from the device, from the user space into our software, we will set the bit. And when we pick up the address, either return address or function pointer, if the bit is set, we know that our data has been tainted, so we should not use it. Okay, got the idea? Okay, let me try to explain this. I add a bit to the memory. If this bit is set, that means it is an input. Okay, let me give you a real scenario so you can understand. Let's say you want to poison me. You want to poison me with water, for example. So you may bring me a bottle of water and hand it to me. Professor, this is a bottle of water I would like to offer you. For example, with these architectures, I would say, oh, you give me water. So I put some color into that water. Maybe red colors or something like that. You give me bottle of water, I put red color, red dye on it. So I put the color in. And when I want to drink something, I pick up maybe my bottle. If I see red color, that means, oh no, it's derived from waters that somebody gave me. It's not my water. Okay. I see the color, so it's not my water. So I will not use it. The same idea. I modify the processor that whenever we have input, meaning passing to kernels, and we have this bit set, if I pick up a return address, oh no, this bit is set, that means it's derived from the input, so should not use it. Same thing, I pick up a function pointer, and I see, oh, the address is set, the bit is set, so it's derived from input, I should not use it. Got the idea? Again, it's like you give me something, so I put color on top of it. If I pick up the data, oh no, it's got color. It's not my data. So I should not use it as my control data. Simple as that. So anyway, we got so many solutions for buffer overflow. I should say so many proposals for buffer overflow. But why we still have buffer overflow today? Anyway, just you may see from the slide there are several lists of several pages of slide to talk about different solutions, but I just put it in so that if you want to see more details, you can just go for it. Okay. Anyway, you may see that several solutions against buffer overflows attacks, they may not work, or people may not use it. Why? Simple answer is some of them they just provide partial protections. Some of them it's like no protection at all, easy to bypass. Or some of them like the canary, they add the canary to protect the address, but there is nothing to protect the canary itself. So it wouldn't work. Or some solutions, they are so expensive, so people don't want to use it. Some solution, they may even have compatibility issues. And several years ago, Intel got something like they call TCPA. I'm not sure whether you're familiar with the term. Anyway, if you do not familiar with the term, just forget about it. But modern computer like your computer, they got a special chip they call TPM, Trusted Platform Module. Well, it has nothing to do with buffer overflow anyway, but for some reason, several years ago, people say this is a solution for buffer overflow. So I have to say something about it. It's just encryption module that comes with your computer. So special kind of encryption. Okay, so let me try to wrap up a little bit. So why we still have buffer overflow today? Because the proposed solution, they may not work, meaning they have insufficient assumptions or they have not enough protection. The second issue is the performance. Some solution, it works, but so. You trade performance for securities. And people don't like that. Just ask yourself, you would buy a faster computer or you would buy a more secure computer? Most of the time you would say faster. Some solutions, they've got compatibility issues. And some solution is so expensive, or it has to change the way that we work, or deploy a new system or new kind of processor. And people don't like that. Okay, I'm gonna skip this. All right, let me ask you this question. I told you that if you use Java or Python or any type-safe programming language, you should be secure against buffer overflow. But in reality, we still have buffer overflow in Java, in Python, in several programming languages that claim to be type-safe. Why? Wanna guess? We still have buffer overflow in Python, in Java. Even though we have bound checking in the runtime system. Why? Well, that's simple, because even though it's Java runtime environment or Python runtime system, they are created in C. And whenever you optimize Java or Python, they call C library. So most of the time when we have buffer overflow, it's overflow down there in the runtime environment, not in the language itself. Because we have no underlying infrastructures to protect against buffer overflow. So it's there in the computer. Okay. So few years ago, people say then, why don't we create all software in type-safe programming languages? Starting from the BIOS, the kernel, the share library, device drivers, everything. Recreate everything. Maybe in Java, in Python, something like that. So that way we can eliminate buffer overflow. You think it is a good idea? No. Okay, so the downside means we still have buffer overflow nowadays. But again, it's getting better. The tools is getting better, and we have less buffer overflow attack nowadays. Okay. Anyway, this is the details. It's not that important. Learn about this. Okay. Okay, just skip this because it's a part of my thesis anyway. Anyway, my thesis is hardware against buffer overflow. So this is just the demo from my thesis. So You can ignore that. And I think that's for the slide today. Okay, any questions about the lectures today before we move on to the activities? Take that as no. Okay, can you hear me now? Okay, again, for exercise number 1, just run the software and you will see list of address. And just so you know, your code, your address would be completely different from my address. Why? Because now we use different versions of operating system, different versions of compilers, so on. So it would not be the same. It depends on the version of operating system, version of compiler, version of shell library, and several things. We got completely different environment, so you will not see the same numbers. But the concept is still the same. Okay. And again, for exercise number 2, we see only one call to greeting in our code. What I want you to do, I want you to overflow the return address of concat argument with the address of greeting. So this is quite simplified because you don't have to inject malicious code. You just change the return address to call greeting, which is easier. So this is the easy version of buffer overflow again. Just want you to understand the concept. So if you got it right, you would got to return. Share the screen again. You would got to greeting. And for the last one, I ask you to emulate an internet service. And you would run one with the cat as a victim and try to pass a message to it. Okay, quick demonstration of this is like this. Again, this is the old version, but the concept is still the same. Here we got a code like this. And you can just if you got it right, you would see this on your screen. This is how it works. You may see that I got a function here, shell. But if you look at the code, you would see that I have no reference or no function call to shell at all. So what happened is that we now try to overflow the return address of this function to the shell function. Return to shell, basically. So I ran it and I got a shell. See, 2 shells. Okay. And for number 4 and number 5, it's just number 4 is the bonus. If you can do it without turn off the canary protection. And number 5, you just answer the question. So again, it's difficult if you are not familiar with stack layout, if you are not familiar with C programming language. And even though you're familiar with architectures and C programming language, it is still difficult because it's now you interact with the underlying system, with the assembly, with the low-level machine. So take some time to do it. It's not just that, oh, you can run it in a few minutes. No. In the past, some students take few days
just to get it up and running, to get it work. Okay. All right. Since this is next week is examination week, so we will not have a class. So I help you a little bit. You got 2 weeks for this exercise, for these activities. You got 2 weeks for it. Okay. All right. Any questions about activities in the lecture today? Again, try to do it, because if you understand it, you understand viruses and worms. Okay, we have question from home? No. What we done? Okay, more questions. All right, from home, do we have questions? No? Okay, so I think I stop here. All right. I see you in next 2 weeks, okay? And for those of you who joined the class today, make sure that you do the participation checks before you go home, do the attendance checks before you go home. Okay, that's it for today. Thank you, and see you next 2 weeks.